Welcome to Civil Engineering for Learners. By Dr.K.Aravinthan. Waste Management. Sanitary landfill. The term landfill generally refers to an engineered deposit of wastes either in pits/trenches or on the surface. The purpose of landfilling is to bury or alter the chemical composition of the wastes so that they do not pose any threat to the environment or public health. Landfills are not homogeneous and are usually made up of cells. The barriers between cells generally consist of a layer of natural soil, clay, which restricts the downward or lateral escape of the waste constituents or leachate. Landfilling relies on containment rather than treatment for control of wastes. If properly executed, it is a safer and cheaper method than incineration. The 4 minimum requirements for a sanitary landfill are: 1. Full or partial hydrological isolation. 2. Formal engineering preparation. 3. Permanent control. 4. Planned waste emplacement and covering. An environmentally sound sanitary landfill comprises appropriate liners for the protection of the groundwater from contaminated leachate, runoff controls, leachate collection and treatment, monitoring wells, and appropriate final cover design. Landfill gas emission. Landfill gas contains a high percentage of methane due to the anaerobic decomposition of organic matter, which can be utilized as a source of energy. We can predict the amount and composition of the gas generated for different substrates, depending on the general anaerobic decomposition of wastes added. Climatic and environmental conditions also influence the gas composition. Due to the heterogeneous nature of the landfill, some acid phase anaerobic decomposition occurs along with the methanogenic decomposition. A typical landfill gas contains a number of components such as the following, which tend to occur within a characteristic range. Methane. This is a colorless, odorless, and flammable gas with a density lighter than air, typically making up 50 to 60% of landfill gas. Carbon dioxide. This is a colorless, odorless, and non-inflammable gas that is denser than air, typically accounting for 30 to 40%. Oxygen. The flammability of methane depends on the percentage of oxygen. It is, therefore, important to control oxygen levels where gas abstraction is undertaken. Nitrogen. This is essentially inert and will have little effect, except to modify the explosive range of methane. It is difficult to convert the amount of gas measured to the maximum landfill gas production value because gas is withdrawn from a small part of the landfill only, referred to as the zone of influence during measurement. Hazards. Landfill gas consists of a mixture of flammable, asphyxiating, and noxious gases and may be hazardous to health and safety, hence the need for precautions. Some of the major hazards are listed below. 1. Explosion and fire. Methane is flammable in the air within the range of 5 to 15% by volume, while hydrogen is flammable within the range of 4.1 to 7.5% in the presence of oxygen, and potentially explosive. Fire, occurring within the waste, can be difficult to extinguish and can lead to unpredictable and uncontrolled subsidence as well as the production of smoke and toxic fumes. 2. Trace components. These comprise mostly alkanes and alkenes, and their oxidation products such as aldehydes, alcohols, and esters. Many of them are recognized as toxicants when present in the air at concentrations above occupational exposure standards. 3. Global warming. Known also as the greenhouse effect, it is the warming of the Earth's atmosphere by the accumulation of gases, methane, carbon dioxide, and chlorofluorocarbons, that absorbs reflected solar radiation. 4. Migration. During landfill development, most of the gas produced is vented to the atmosphere, provided the permeable intermediate cover has been used. While biological and chemical processes affect gas composition through methane oxidation, which converts methane to carbon dioxide, physical factors affect gas migration. The physical factors that affect gas migration include environmental conditions. These affect the rate of degradation and gas pressure buildup. Geophysical conditions. These affect migration pathways. In the presence of fractured geological strata or a mine shaft, the gas may travel large distances unless restricted by the water table. Climatic conditions, falling atmospheric pressure, rainfall, and water infiltration rate affect landfill gas migration. If the escape of landfill gas is controlled and a proper extraction system is designed, this gas can be utilized as a source of energy. If landfill gas is not utilized, it should be burnt by means of flaring. However, landfill gas utilization can save on the use of fossil fuels since its heating value is approximately 6 kWh per cubic meter and can be utilized in internal combustion engines for the production of electricity and heat. It is extracted out of the landfill by means of gas wells, which are normally drilled by auger and are driven into the landfill at a spacing of 40 to 70 m. In addition, horizontal systems can be installed during the operation of the landfill. The gas wells consist mainly of perforated plastic pipes surrounded by coarse gravel and are connected with the gas transportation pipe with flexible tubing. The most important factors influencing the planning and construction of landfill gas extraction systems are the settling of waste, water tables in landfills, and gas quality. Leachate formation. Leachate can pollute both groundwater and surface water supplies. The degree of pollution will depend on local geology and hydrogeology, the nature of waste, and the proximity of susceptible receptors. Once groundwater is contaminated, it is very costly to clean it up. Landfills, therefore, undergo siting, design, and construction procedures that control leachate migration. Composition and properties. Leachate comprises soluble components of waste, and its degradation products enter the water as it percolates through the landfill. The amount of leachate generated depends on water availability, landfill surface condition, refuse state, condition of surrounding strata. Common toxic components in leachate are ammonia and heavy metals, which can be hazardous even at low levels if they accumulate in the food chain. Leachate migration. It is generally difficult to predict the movement of escaped leachate accurately. The main controlling factors are the surrounding geology and hydrogeology. Escape to surface water may be relatively easy to control, but if it escapes to groundwater sources, it can be very difficult both to control and clean up. Control. The natural and geomembrane liners are often combined to enhance the overall efficiency of the containment system. Some of the leachate collection systems include impermeable liner, granular material, collection piping, and leachate storage tank. Leachate is trucked to a wastewater treatment facility. Treatment. Concentrations of various substances occurring in leachate are too high to be discharged to surface water or into a sewer system. These concentrations, therefore, have to be reduced by removal, treatment, or both. The various treatments of leachate include leachate recirculation, biological treatment, physicochemical treatment. Thank you. Happy learning. See you again.